It's always a pleasure to discuss actigraphy, and you will see that I very much like the technique. And I have the feeling that, like when I arrived in the lab, as you said, I transitioned from another field, and then everything was new for me to discover. And then I realized that actigraphy was maybe, at least to my opinion, a bit underused, at least in our lab. So it was mainly used to control if participants were compliant with the protocol of different studies prior to, like the in-lab study. And we realized that there was maybe more than just this in actigraphy. So we started to develop the tool, and we realized that the tool might be also useful for others. So we started to open the tool to the community. And as you said, that not developing a tool is easy in a sense that depends on your background. You can just develop a software, but I have to admit that, engaging with the community, trying to get to understand what actually other people, people outside of your lab actually needs. So like they can't just pop up in your office and say, look, I need this and this feature. So that's for me the difficult part. So I really enjoyed this kind of the workshop, and I'm really, really thrilled, really happy that you invited me to this. Okay, so let's get started because we have a couple of things to cover. So now, if you allow me, let me share those slides. Okay, so this is going to be the presentation, and you received the timetable prior to the webinar. So normally, I should be giving a quick overview of the current use of actigraphy and sleep and chronobiology research, but what I will do right now is maybe postpone that part and directly jump to the installation procedure, because some people need still to set up the whole environment, it might take some time. So if things are downloading or installing, then we can still move on while it's actually done in the background. So let's move with that. In the email that was sent around to the participant, you should have received some instructions on how to install the toolbox, and also a link to the data sample that we're going to use today. Okay, let's see what happens if I just click on this. And let me see. Okay, so normally you should be directed to the special instruction that we wrote for the tutorials. So if normally everything is successful, you should be in front of a subsection of the installation procedure that we have with the toolbox. This is the online documentation that we set up. It says, well, it contains a lot of informations, and we crafted the installation for the tutorial. The basic of that installation is the use, I mean, the main point of this installation procedure, which is not the one that I was recommending so far, is actually the use of Anaconda. If you can manage, you see, like that's a software that is actually distributed by a company. So I would encourage people that can manage their own environment to do so and stay away from this kind of tool. But I have to admit that Anaconda did a great job in packaging all the tools that we actually need into a single software. So if you want to install, especially on Windows machine, if you want to install everything in one go, that may be the way to proceed. That's why we give here instructions to do it like this. So basically, you just have to go to the Anaconda's webpage, download the Anaconda and Python bundle, and install it on your computer. So once it is done, actually it will install two ingredients that are needed for this workshop. The one is the Anaconda prompt. So it's actually a terminal where you can run the command lines that we copy pasted here in the instructions, and also a navigator that is actually for which we provide a screenshot just a little bit down the instruction, where you can launch the different tools that have been installed within Anaconda. And one that is extremely useful for that workshop is the Jupyter Notebook, because all the tutorials that I will show you now are actually notebooks that you can run yourself. I will run them interactively, but actually they are contained within the package, and they are also available on the GitHub repository of the package, and you can just download them. And if you have a Jupyter Notebook server, you can just run them. You can also practice with the data sample that we send around for this workshop, but you could also practice with your own data. And there are also data that is actually shipped for testing purposes within the package. Now I see that there is already. Okay. Okay, so good so far. I hope that the instructions were clear to everyone. Maybe a little bit of details here if you're not familiar with Python. I hope you are. I see that someone is there also asking for instruction link. Basically, what I would recommend is whether you manage your own environment or if you use it with Conda is to create a virtual environment. So these virtual environments, basically what they do is that they will contain or isolate the Python installation from the rest of your computer, because you might already have a Python installed. And everything it does is that it creates a small environment which is isolated from other environments that you can set up. And here you will install all the different packages that you need. So if you need different packages at different versions, they won't conflict because you can switch from one environment to the other. That's why here we recommend to create a special environment just maybe for this workshop, where you will install the different packages that you need. And once it is completely set up, then you can install the pyActigraphy package with this command. If you already have, let's say, a functional Python environment, that becomes even easier. You can just use the official Python package installer pip, and then just doing this Python -m pip install pyActigraphy. This will download the package, install it, and also install all the dependencies. Okay. So now, if you are successful in running Anaconda, creating your virtual environment, you need to activate it so that you are within this environment, and all the packages that you will install will be within this environment. Now you can install also Numpy. We have set up a specific version to avoid conflicts between different dependencies. And then once you have installed Numpy, then you can install with this command. With pip install pyActigraphy, you will install the package. Okay. So normally, if everything runs smoothly, you should have a special virtual environment for this tutorial with all the packages that you need installed. Now that you have this, you can also maybe launch the Anaconda Navigator. So this is also something that you can do normally if Anaconda is successfully installed via window. There is an application menu, I think, on the bottom right-hand side, or left-hand side. And then you can type Anaconda Navigator, and then you can launch it, and then it will pop up, and it should look like this. Normally, if you are running on Mac or on Linux, then you can just open a terminal, and then if all the paths have been set up correctly, you can just type Anaconda Navigator, and this will also launch the navigator. Now the small, this is why we set up a warning, and I couldn't find a way to have a big warning in red here, but that should also be worth noting, is that if you launch application via this Anaconda Navigator, you should be careful in launching the application from within the right virtual environment. In our case, this is the pyAct39 that we set up before. So you should pay attention to select this environment, and then once it is done, then you can launch the Jupyter Notebook. And if you are successful, normally you should end up with a server that actually looks like this. So it allows you to navigate through your file system, and then if you find a notebook, you can just click on it, and then it will launch the notebook. Okay. So now let's go back to yes. Okay. So hopefully, normally your environment is fully set up. You have the pyActigraphy package installed. You have the Jupyter Notebook server up and running. And now what you actually need is the actual notebooks. So those notebooks, as I said, here I provided links just to make life easier, but actually they are located within, if you go through the architecture of the package on GitHub, you will see that within the documentation, In source, actually, you do find all the notebooks here, all the files with an extension, which is pyNotebook. Those are the notebooks that you can use. Actually, those notebooks are turned into the online documentation that you will find also online. And the link is actually also here on the GitHub repository. So if you click on it, then you will end up in this online documentation that contains tutorials. Actually, those are static page, but actually that you can access online. But if you want to practice, you just have to find the corresponding notebook and you can actually run it yourself. So that we found that was a nice way to maybe let's say help people to learn how to use the toolbox. Okay. So now let's go back to the end of the instructions. So if you can download, I would suggest that you would download this. So this is what I did. I downloaded all those notebooks. You can find them, then you can navigate to a location where you store them. I suggest also that you have somewhere in the directory also the data that we are going to use for this workshop so that you can easily navigate through them. Okay. So now that you have the different notebooks, I suggest that we go back to the presentation. Okay, let me go back. Okay, here it is. Now we are back. Okay, so maybe I will give or let people try to install, and then in the meantime, then we can just briefly chat over the use of actigraphy in sleep and chronobiology. There are plenty of resources. The NSRR is running also blog posts, you see like, and then you can find also information in there. So I didn't cover those because you can easily find them. So I will just give you maybe just a few words on the actigraphy. Those are, it's my personal view on it. And I selected also among the many applications that you can have in actigraphy, I selected the ones that I find are interesting, but those are not the only ones. Just for the sake of time, I just had to select a few, but there are plenty of applications. Okay, so let's quickly cover. I suspect that all of you know, if you're subscribed to an actigraphy workshop, you should have a brief idea of actigraphy already. But let's start with something basic. So what it is a continuous measure of the activity. It is, and nowadays, the movements are measured by accelerometers, and usually it's worn at different locations depending on the purpose. In sleep and circadian research, it's more like on the wrist. If you are also more in the physical activity research realm, you might find also other placement like the hip or the chest, so that you can also calculate maybe more the engagement of the body if you're interested in the physical activity. So basically what it does here is just an example of one device. So it's a small watch-like device that you can wear at the wrist, for instance, and then it will continuously measure the acceleration through the accelerometers that are contained inside. And then basically there are some post-processing that will give you access to counts. The counts will reflect the intensity and the quantity of the movement. But nowadays, and that's also good because you see like this processing is specific to the device. So if you are running two different brands or device types, then it's hard to compare. So the comparability and then across the different devices and brands, it's really, it made a hard time for us to try to pull data together. Nowadays, with there are more and more devices that let you access the raw data, the raw acceleration. So, but then it's up to the user to post-process this acceleration. Fortunately, for instance, with the Activity devices that have been used for the UK Biobank, they also have softwares that allow you to also calibrate the data and also reconstruct. And the good point is that if you have access to accelerometer, maybe there are differences between the devices, but if they're well calibrated, normally you should be able to compare data, even though they have been acquired with different devices, if you can just track quantities that are physically meaningful, like the acceleration, and then it gives you something with a unit which is in G. So basically, once you have This you end up with a time series that actually reflect the physical activity over time. And this is what I presented here in that graph. You will see that anymore. Each time that we discuss with we discuss actigraphy, especially in a sleep lab, it's like there is always something that should be discussed, I think, is that we discuss what it is. And I believe it's important also to tell right now what is this not. Actigraphy is a measure of the locomotor activity, and you can do plenty of it. And but the thing is that if you obviously, and that sounds like maybe something obvious to say, but I think it's important to say, it is not a way to measure sleep, especially because if your definition of sleep is a brain EEG centric definition, so based on the cortical activity of the brain, then obviously that's something different. It might be related. You might infer wake and sleep from locomotor activity. There is a connection between the two, but it's only an inference. So there is always ambiguity. It's like if you look at the picture that we put here, is that if you don't move or if you stand still in your bed without moving, in the dark, you see, like even if you have a light sensor on top of that, you cannot distinguish someone sleeping from someone that is standing still. So notably, you see, like there are plenty of studies showing that, in the case for insomnia, for instance, that's really not known, that it's extremely difficult to run actigraphy studies for this kind of sleep pathology, for instance. Okay, so it is not sleep, but you can infer wake and sleep patterns. Okay, so let's see. That's now that you see, like we discussed the fact that it's different. Let's see what we can actually do with actigraphy. So if you have been running EEG experiment, you will see how hard it is. So that's also something. Let's see that actigraphy can be a nice way to complement. And as we said, it's ambiguous in the terms of detecting sleep and wake, but still, I mean, it offers new possibilities, especially on the scale to which you can deploy this kind of technique. That's really something which is some devices are really cheap and that are easy to use, so you can actually deploy those things on a large scale. And this is one of the well, not so recent, but recent study where they actually use which is like a small accelerometer that is actually a ring, and it has more than just accelerometry in it, but they used also that to infer sleep. And what you can get from that is that they had access to data that were collected online from 200,000 users, and they had access to, on average, like 250 nights per user. So it's like 50 million hours of sleep that they could access. And then they did that worldwide, and then they could spot differences. Yes, like depending on the continent, or let's say the community you belong to, they could actually spot differences between what they would say are not rest duration, but sleep duration. And then they could also look at the timing, the duration of sleep, the timing differences between week and weekends, the so-called social jet lag. So, and that they could infer that on a scale that is really, really impressive at that moment. So you see, like that kind of opportunities. Obviously, it's maybe if you are really from a sleep field, then you will find that obviously there is sizable differences. And then when you see studies trying to compare PSG with actigraphy, then obviously there is always a bias between the two, especially, like trying to find when people get their sleep. But if you are able to live with this kind of ambiguity, you can also get large numbers and then try to derive information from the population. Okay. Another example is also something like if you want to access the genetic of sleep. For this, you need a lot of participants, and this is exactly what they did. So see, like again, they use accelerometry, they derive sleep from this, and they use a bit less than this 100K of participants from the UK Biobank who had actigraphy recording for 7 days, and then they were able to identify new genetic association between sleep quality, sleep duration, and genes. So that's the kind of things that also requires a lot of data, and that's where actually actigraphy might be handy. Okay. There is also something else that actually I do like is that, and that's more specific to actigraphy than just sleep, like rest at night. Here is more like, since you have the whole pattern of activity, you can just track this kind of rest activity pattern. And then this is actually the timing of the two, which is important. And then you can try to create this kind of double plots. So basically here is nice to see like the 2 consecutive days are actually plotted on the same line. And then you see in between, you can track, you see a period of activity, and then you see like there is a period of inactivity and then activity again. And then with this kind of display, you can track actually the stability of the pattern. And what is interesting, and this is what we're studying at the moment, is if you have been doing EEG acquisition in infants, you know how cumbersome it is. So then you realize that actually using actigraphy, especially in pediatric population, is really, really handy. And this is something that has been done, obviously, in the past. It's like this one is quite an old paper already, but this is really beautiful because you can track, and then you can see the pattern from day one in infants up to 6 months. And then for some infants, it was over a year. So there is no way that you could actually do that with EEG. So if you want to really follow this kind of a sleep wake pattern, then actigraphy is really handy. These graphs are beautiful because you can see the installation. So there is already, since almost day one, some kind of alternance between our differences between day and night activities. But you can see that as time goes by, you can see that indeed it becomes more marked, and then the circadian rhythm is established. So you can see that in all the different infants that are presented here and these actograms. And that's something that is really unique to the technique. And then you can study really in situ the developmental, let's say, maturation of the rest activity, the circadian rest activity pattern. So that's something that is also kind of interesting, I think, with actigraphy. Okay. Okay, so now it's done. That was my just brief overview of the things that I find interesting, but not only, but a few of them. And now what maybe we should move to is to give you a little bit of a, let's say, a sense of how the pyActigraphy software is built. That might be useful because just like if you have questions, just like we have set up an online documentation on different functions, but sometimes you really need to understand how it was, how the architecture is set up so that you can actually dig into it and find a solution yourself if there is a function that you want like to use, which is not, at least that doesn't contain the right information. Okay. Starting with a brief overview, so pyActigraphy is a Python package hosted on GitHub, so you can always see the code. It's open source. It is released under the GPL3 license. We were fortunate enough to be able to publish software, which is not always easy because you can develop softwares, but publishing software is always more difficult. One thing that is, I think, important, because when you discuss open source softwares, and that was also briefly mentioned by Mike in the introduction, is that when you use open source softwares, it doesn't mean that it's not proprietary, and sometimes it might be that you have a whole team, like like the standard packages in Python, they have like almost a whole society of developers behind the scene. So actually they are and millions of users. So you say like those you can easily rely on and trustfully use those packages. When you use packages that have been developed by like individuals, that becomes a bit more difficult. You need to gauge on the quality of the software. So a software that has been published already is already a good sign, but it doesn't mean that it's not published, that it's not a good software. But there are a few things that you should gauge. Is it actively maintained? Is it used by many? If it's used only by 1 or 2%, you say like maybe that's something that you should consider. But something that you should also consider is it tested? And this is what we spent quite some time developing this in pyActigraphy, is that we have unit tests. And actually at the moment we have 160, which means that actually each time we develop a new feature, we run all those tests to see if we are not introducing by accident any bug. Also, it allows us to test if the implementation of specific variables is actually accurately done. It's like for some variables, if you have the analytical expression, you can calculate the expected values if you input a certain signal, and then you can have a synthetic signal as the input, and then you can test the output. And this is precisely what those tests are. And then in some variables, and that I will discuss later on, you see like we were able to say, look, okay, it should be, if it's a sinusoid as input, it should be a value of 1. If it's a white noise, it should be a value of 0. And this helped us to test. And we are expanding. Each time we develop a new feature, we try to associate those new features with tests. So that should also give you some confidence. Obviously, there is no software which is not bug-free, but at least it gave us some confidence in the implementation of the pyActigraphy package. Okay. Concerning the documentation and the tutorials, as I mentioned already, they are online. Just go to the GitHub page and then you will see all the links are there. Okay, now just to continue with the brief overview, there are different submodules of the pyActigraphy package. There is one which is called IO. It's just to read the different formats. There is a visualization that would definitely need more. I'm not really an expert in like visualization, and I tend to more calculate things than visualize things, but definitely useful. So that's also a good thing. If people are willing to help, that would be a nice package that actually needs to be expanded. And there is a cleaning that we will cover, a cleaning submodule that we will cover. There is the automatic sleep rest activity scoring with different algorithms. There is also a module for non-parametric methods calculation. And then some functional linear modeling that we implemented, and also a module also helping people to analyze the locomotor activity during sleep. Okay, so all this is contained within pyActigraphy at the moment. Now let's go through the different functionalities, but because we will not cover all of them during the tutorial. As I said, actually we have a unified interface to read different Actigraphy formats. We are going to use within the workshop a specific one. We have the data that we circulated. Those are actually data that emulate the MESA dataset file format. But actually, you see, like you would ingest with a specific function, but you can ingest, if you have data from other devices, you can also ingest in the same way with different functions. And then you will see that the syntax is almost similar. So we are able to read multiple file formats. So from ActTrust, ActiWatch, from Command-Tech, MotionWatch, Actigraph, also the Respironics devices. And the dactics that have been also used, the Tampati Lumi from C Brazil, and also the raw data from the MESA that I just said. Okay, we can also mask automatically or manually the peridosperse activity. I will show you that in a specific tutorial. You can also visualize your sleep agenda. You can visualize daily profiles. You can also do some signal filtering and smoothing if you're interested in doing some functional linear modeling and analysis. And then it contains also more than just, like visualization, ingesting data and visualizing data. You can also calculate the usual rest activity rhythms, which are quite, let's say, standard in the field. So these variables have been around for quite some time already. And there is also a way to automatically identify periods of rest and activity. You can also calculate something that actually I do like. It's the sleep fragmentation, or activity or rest fragmentation via the state transition probability. It's a analysis performed by Andrew Lim already like quite some time ago, but still it's really extremely useful. To quantify fragmentation. There is also the tools to run the nice analysis of the locomotor activity during sleep that do track the dynamic of the sleep cycles. And also there is a nice signal decomposition technique that I do like, the SSA, that allows you to inspect separately the circuit and interleaved components if you're interested in those subsets of rhythms. Okay, so that's the different possibilities of the package. Now, the tutorials, we will cover some of them. There are more than what we cover today. And they are online if you just want to see them. But if you want to practice them, you can just download the corresponding notebooks and then run it yourself. Here is the link to the online documentation, and then they are available within the package if you download the package. Okay. Just last remark maybe is that if always I think worth to discuss if people want to contribute, and that would be really brilliant. Just like by the past, we always had nice contribution from people. But the thing is that some people sometimes they don't know how to contribute. So, and I think there are plenty of different ways of contributing to a package. The first way to contribute is just to use it and to cite it. That will also show to like our founders that actually you develop something useful, and then if you ask for fundings to let's say maintain the software, that's also make a strong case if you have a large base of users. If you find bugs, if you find issues or things that are not as described, then you can also report the issue. That's really valuable. So you can do that via GitHub. There is a special way to report issues, and that will be that's also a way to contribute. You don't need to be a full software developer to contribute, actually. You can always suggest improvements. That's always good. It helps the package to evolve. And try to acquire new feature, new functionalities, and this is how package grows, and then they are more and more used. If you are willing to extend the doc, because it's like obviously if you are the developer of software, everything seems like obvious. So that's always difficult to write useful instructions for people that are not developing the package. So if you find things that are not clear, or if you want to extend the documentation with a certain use case, that's really, really important, and that would be extremely welcome. And if you don't know how to cite it, there is also the link on the GitHub page. If you use it and you please cite it, you can use it. Okay, so for the workshop, we are going to use data that actually mimic the format of the MESA, the multi-ethnic study of arteriosclerosis. This is a really nice data set hosted by the NSRR. Actually, it's like it was meant to study cardiovascular disease. And the good thing is that they have for a subset of the participants, but a large subset, which is like almost 2,300 participants, they have 7 days of wrist-worn actigraphy. And we are going to use, let's say, 5 files that emulate the file format of those. So if you are able to run those these examples, the different tutorials that I will show you, then if you have access to this data, because you should request the access if you want to have access, then you can just plug the new data, and you don't have to change the code because that's going to be identical. Okay. Now, let's dive directly, because we are already, I think, running late. Oh, no, not that late. That's good. And to the part 2, which is how to read and visualize data with pyActigraphy, which is actually their step 0 that you would like to any kind of analysis. Okay, so for this, here are 2 links. Those are the 2 first tutorials, so the intro and the one for the batch. And those are the first 2 that have been linked into the main instruction, the documentation in the instruction part. So let's switch to that one, actually. So if you go back now to this, okay, and we go to the installation, you see like the intro and the batch were the first 2. So what I suggest is that you download those 2, and then with the Jupyter let's say Navigator, you can browse through your file system, find those 2. And once you have found them, you can just click on one, and then it will open a new it will open this new intro that I have already opened here. Okay. So those, if you have checked the online documentation, you see like this is the online documentation that will show you something, that will remind you something. This is here, the intro. This is basically the notebook, except that here it's static. If you have it on your own computer, you can practice them. Okay, so this is a notebook. A notebook is like a self-contained object with different cells where you can type code. You can also type some instructions or comments and text. You can also display images. So it's actually a nice way to have a narrative on your analysis. And I think it's interactive, so you can easily practice. You can directly see the output of each cell as it is executed. So to start, using it, maybe at the end of the day, if you have an analysis, you may want to have a full script. But to practice, to play around with the toolbox, that's always nice to have something interactive. So I think notebooks are great for that. Let's start. Okay, so as always, in Python, the first thing that you do is you import all the packages that you need. Let's start with, oops, I need to restart the kernel. Okay, now it is. Okay, so actually you have imported the pyActigraphy package. What I'd suggest is that it's always good practice to print the version so that you know exactly what you use. So you can do this by using this print command. And then once you have a package, there is most of the time a way to check the version by checking this special keyword underscore version. And then that tells you the version of the package that was loaded. Here it's 1.2.2, which is the latest one and the one that you should use for this tutorial. Now I import another package, which is not part of pyActigraphy. It's just an external one. It's just for visualization purposes. I didn't, let's say, bundle any visualization package with pyActigraphy because I wanted to let people decide on what they use. Just like crafting, like plots for publication is a real art. So it's really, if you are used to one, you should use the one that you prefer. Here I'm just using Plotly because they provide interactive plots that I like, but you feel free to use whatever you like. Okay, so let's see how we can read an Actigraphy file. Those are actually the different file formats that we read. And actually for each file format, there is a dedicated function. So the function is always like read underscore row because you can read directly the raw data. And then the last 3 or 4 letters, they actually are a way to see to which device and file format they refer to. So here we are going to use the one which is the read row MESA. But if you have, I don't know, Motion Watch 8, you can use this MTN. If you have Respironics, you can use the RPX, and so on and so forth. Okay, so let's now create a small string, which is just the path to the file that I downloaded for this workshop. So here you can just modify the different paths to your and adapt it to the path where you store the actual data for this workshop. Here I put them into this subdirectories under data. You can inspect. This is exactly what it is, and here it is. This is always the entry point in pyActigraphy. You have the package, you have the submodule IO that contains all the readers, and here you're going to use a function that is read row MESA and then the name of the file that you want to read. If you are if you are using the MESA dataset, then it's going to be MESA and then the ID of the participant .csv. And it does what it does. It does read the file and output an object, which is I call here the row object, and that's actually the object that contains the data, and it also contains functions that calculate whatever you like. So this is the entry point of of most of the analysis in pyActigraphy. You do create this, so we created it, and now that row object contains different attributes. So attributes are just a way to access directly data that are contained with this object, and then it also it has functions. So the functions you can easily identify with the brackets at the end of the name of the function. So if you want to check what was the name of the subject that was acquired, you see like we extract within the file the field which is name, name. Are you executing your function? Okay. Here you see like in the notebook, you just have to type Shift Enter. Shift Enter will just execute the cell. You just type the code that you want to see executed, and then you can just type Shift Enter, and then it will enter. It will execute. Then you will see below the cell the output, and then it will move to the next cell. Okay. So now if you want to see the start time of the recording, you see like this recording, but those are obviously fake dates, but it was started on the 5th of January 2000 at 6:30 p.m. And then if you want to access the duration of the recording, you just have to type the duration, and then it's 8 days here in that case. The UID, there is no UID information stored in the file. So here you won't get anything, but for other file formats, you might also get the UID, which is like a unique identifier for the device. And then it helps you to also link the device that was used. So if you have malfunctions, then you can see, okay, look, I have issues with my file, then I know that it was because I'm using that specific device, and maybe you don't want to use it anymore. So it might be handy to access it. And then the frequency here is the sampling frequency, so which means that you have a point in your time series of activity every 30 seconds. Okay, so those are just information that usually are contained within the header of the different files. And actually, they are useful if you want, let's say, to perform the analysis, you need to know from which subject has been acquired. And also sometimes you need to be careful of their sampling frequency just to pull data together. Okay. Okay. Let's now move on. You see, like you can use different. I'm going to show you how to plot data with the Plotly package, but you can see it's easy because you see, like once you have access to this raw object, maybe I will show you something here. Is that actually you see like there is a field which is data, and actually the data is actually a data frame. So and data frame, the concept of data frame is like it's not only in Python. There are in R. I think they are calling it the same. It's like it's a tabular data. That you can easily manipulate. And this has been, like translated. We extracted the data from the file, and then they have been ingested in terms of a data frame. So if you know how to manipulate data frame, which I suggest that you learn how to do, because that's something that you might be handy for during a PhD, for instance. Then you can do whatever you want once you have access to the data. We provide different functions to calculate things out of this data, but you can always access the raw data behind with this. So if you have this, then you can easily plot those data. Okay, so here I'm using the Plotly package. I just defined a layout, and then here you see like I will just display a scatter plot with the index as the time index as the X values, and then the raw data as the Y values. And then you see like this is precisely what we said. This is the time series of this first file. And this is the time series as a function of the time. Okay. And then you can see obviously the circadian modulation of the activity every day. Okay. So now we are able to visualize, and that's an important step. It seems silly like this to visualize the data, but you see like, and that's going to be covered in the next tutorials, but the visualization and the cleaning is the most important part. You see, like you will see that calculating variables, that's easy. It's one line of code, but actually it always depends on the quality of your data. So you need to visualize the data to assess the quality, and that will influence your analysis. So basically visualizing and cleaning is a really, really important step. So you should always start with that, and we provide the tool to do this, okay? What could be also nice to look at is the daily profile. So it means that you average the activity across multiple days, across all the days, and then you give their average activity patterns over 24 hours. So that's also quite informative on the pattern of your participant. Okay, and here it's as simple as once you have again the raw data, the raw object that contains the data, you can just call the function average daily activity, and then contains some input arguments. And if you don't exactly know the signature of the function, you can always type help. This is how you get help in Python, actually. You see, like if you want to look at the documentation of the function, actually you can always type help, and then it's going to display the documentation. So it's actually the inline documentation. So it's really within the code that we set up this documentation. So it tells you how to use that function. So here you see it tells you what it does and what are the input parameters. So frec is the data resampling frequency that you want to use. If you want to point every hour, you just put 60 minutes. If you want to have something cyclic, which is like if you want to have this kind of double plot, here you have to set up this option to true because it's a Boolean. If you want to binarize the data, if you just want to say, look, I don't care if it's a count of 10, 20, 100. If it's above a certain threshold, here it's there, you can set up, you can customize. If it's above a certain threshold, put a 1. If it's below 0, you just discretize, you binarize the data like this because you're just interested in, am I active, not active? And then time of origin is just to set, like the time axis of your plot. And once you have this, you created it, I store it in a certain variable, and then this daily profile again as an index and some data, and I can just simply plot it. And this is what it does. You see, like this is the daily profile of my participant on a 15-minute basis. So I have a point every 15 minutes. Now, if I'm interested in a more coarse description, I can just modify, say, 60 minutes, and then you can replot, and then you have a plot every hour. And then you can see the pattern of that participant across the day. Okay. So that's it for the visualization of the data. It is just a small introduction. You can use the whatever package you like. But here is like it's just more. That's why we use, because you see like it's interactive. It helps you to maybe zoom in, zoom out, inspect some periods that you want to maybe where you want to have a more careful look. And get there, let's say, a feeling on maybe the participant compliant, like with the protocol or not. So those kind of things that you might want to see. So might be useful to have an interactive plot. That's why we use Plotly here. Okay. There is also something here, but it's more like anecdotal. It's like we try to set up, let's say, a way to detect the activity onset and offset. And at the moment is really coarse because we wanted to have a way to define, like periods of activity and periods of inactivity based on that profile. So we wanted to have something, but it's really coarse at the moment that would need some more refinement. And also there is a way also to, let's say, to detect on a daily basis the rest period automatically. So there are dedicated algorithms for that. So it's maybe less useful, but still it might be useful to get already an idea of the mean onset and offset of the data. So we have created two variables, which is activity onset time and activity offset time. And that gives you some time, some ideas on what you can use to say, okay, look at that period, the person will be active and then inactive. Okay, so that's it for the moment for the introduction on the visualization. I don't know if there is a question so far. Nope. And yep. And just a small mention that I have an extremely good friend next to me that is already answering almost all the installation issues. So thanks to him, we have now time to move to the second tutorial. Okay, so that's it for the this one. You can practice. The thing is that if you want to practice with your own data, you just have to change the path. You point to your own data. You can read. Just be careful to change this function according to the data file format that you want to read. But actually, you see, like that's not more complicated than this. Actually, in the original version of the tutorial, there is it's not that complicated, but there is a way to access. Wherever you put your toolbox, there is a way to always access the files that are inside. And actually those files that you can see here, maybe I will make a small editor in test data. This is the data that I use for the internal test, but you can also use them to just practice. So you see, like I have files that are from ActiWatch, from Common Tech, and there is also data from Actigraph, Respironics, Common Tech Motion Watch 8, and the ActTrust data, for instance. So you see, like all those things, you can always use them just to practice. And actually, you can just replace the name of the file in the original tutorial because the path will always point to the test data if you keep the way it was formulated originally. Okay, just have to change maybe the reader function. Okay, so it's as simple as that. Once you have ingested, you have your raw data, your raw object, sorry. The rest of all what I'm going to show is exactly the same. So that's really the entry point of the toolbox. Okay, so let's shut down this notebook. And now we try to move to the next one. Okay. So this was for the visualization. Now, the second part is, let's say, to give you an idea on how to clean the data with pyActigraphy. This is maybe the least sexy part of any analysis. But yet, this is most likely the most useful one. I hope at the end of this tutorial, I will basically succeed in convincing you that it is really, really important, and because we'll see that it might impact the metric that you're going to calculate. So that's really a crucial part. That's the most boring part, but that's the most crucial part. Okay, so for that, there are different issues in cleaning. So we have two different tutorials, two different notebooks. One is called pyActigraphy masking, and the other one is this SST log. So it stands for start stop log. And I'm going to illustrate those two. So let's start with the masking one. Okay, now we are back. Okay, let's move. So again, you see, like advise you to go back to your Jupyter server. Then you can navigate through the different notebooks, and then you can just click on masking, and then masking will open this notebook, and then we can practice interactively together. Okay, as in any, again, oops, need to restart the kernel. Okay, now it starts. You need to import pyActigraphy. Again, we are going to look at the data. So I import my favorite plotting package. And then again, the same. I'm just changing the path to point to the tutorial data. And I'm going to use this time the subject tree just for illustration purposes. So you see, like, again, I ingest the data of subject tree with this read row mesa function, create the row object. And once I have the row object, I can use it to actually plot the data. Up and then up now. Here it is. This is the data that we have. Now, when you look at this, and that's why it's important to have let's say an interactive, let's say plotting tool, is that you can zoom in and zoom out, because it's like sometimes what happens is that people, and for various reasons, sometimes they have to remove their device. Which means that actually but the recording is still ongoing. So which means that actually you have a stretch of data that does not represent the activity of the participant. Maybe because you see, like, some devices are not especially waterproof, so people tend to remove it when they go to shower, when they go to the swimming pool. So you see, like, there are plenty of reasons why you just remove things. And you don't want to analyze this data, because it's not the data, it's actually zeros, it's inactivity, but that's not the inactivity of the participant. So you see, like, imagine that you consider that this part, oops, not this one. Let's look at maybe this one. Is it the 12? Let's go to the 8 of, here it is. Yes, imagine this one. Here, there is a sharp transition. You select to activity. There was a sharp decrease. So maybe someone just removed its device and you said, look, I don't want to analyze this. And that's something that I should actually exclude from the analysis. So we have a mechanism for this in pyActigraphy, is what we call masking. And that's something we never touch the original data. That we just create on top of the data a mask that is actually used in any processing done within pyActigraphy. If there is a mask, it will always be used. You would just have the opportunity to turn on and off the mask if you want, but that means that the raw data is untouched. So that's why it's so easy to remove actually the masking. So to remove the masking, imagine that you have here, maybe you can argue that it is maybe just a nap or maybe, but imagine that you have good reasons to believe that this is some spurious inactivity because maybe you have a sleep agenda where the participant actually explicitly said that he removed the device. So just for the sake of the illustration, we're going to consider that we want to mask this. And here it is. That's the definition. For us, it's a consecutive stretch of consecutive zeros, and that's a mask. So there are two ways to do it. Either you can say, look, I want to create a mask automatically. So it will spot any stretch of so many minutes of zeros. And here you can configure that. So here you can say, look, everything which is like total inactivity. So no spike, no, just a stretch of zeros for 2 hours. That's going to be something that I want to mask. So you can actually create the mask like this. And then you can inspect the mask. Okay, the inactivity length was indeed 2 hours times, like the number of points per minute. Here it's like 2 points per minute because you have a sampling frequency of 30 seconds. So which means that over these 2 hours, you have 240 points, which is good. So this is exactly this inactivity length. And then let's see if we can visualize the mask. Once you have created the mask is always accessible through a simple row mask. And again, that's just a time series. It's again tabular data, pandas series behind the scene. If you know how to manipulate the data, the pandas series, standard package in Python pandas. If you know how to manipulate that, you can do whatever you want. Okay, so here we can just access again the index, which is the timestamps, and here the Y is going to be the data. So we can just visualize the mask. So here, the convention within pyActigraphy is that if you don't want to mask something, the mask is set up to 1. It's actually a convolution between the mask and the data. So if you just multiply your data by 1, you don't change the data. But actually, if you just set the value to 0, those points here, actually, those points that are set to 0 in the mask, those points are those that's going to be masked in during the analysis of the data. So automatically he found a stretch of 2 hours of zeros and said, look, I'm going to mask those two. Okay, so it was automatic detection. It works. Well, it works. But you see, like, this is usually when you see it, this obvious thing, that's easy to spot. What you want also maybe to do visually is that when there is, like a small bump, because I don't know, the device was put somewhere and then still moved, you want maybe to gauge visually. So you want maybe to adapt those things. So here is the automatic way is just for unambiguous situations where it's just a stretch of zeros, no movements, easy to detect. Now, if you want to detect more, there are maybe a few algorithms on the market, but they are always specific to the different devices. There is no universal, let's say, spurious activity detector. Maybe that's something that we should work on, but to my knowledge, there is none. So most of the time, if you want to have a quality masking, then you have to do it also by hand. So, or at least complement the automatic detection. So we have a mechanism within pyActigraphy to let you do this. If you want, you can still build up on the one that you created like this automatically, or you can start from scratch. So if you want to start from scratch, you just set up the inactivity length to none again, and there is no mask anymore. And then you can add manually the different period. Now, if you say, look, I want to mask that period, then you just had to say, look, that's my row object. I will add mask period and start at that time and it stop at that time. Okay, so if you do it again, okay, that's going to create a mask period. And you can add as many as you want for a given participant, and you can mask. And sometimes if you have really, really long recording, this is what's going to happen. You're going to have like multiple ways. If also, especially if people have specific patterns, just like if someone goes to the swimming pool every week, or if the participant removed the device during shower, then you might see something every day. So there are things that you might want to mask like this multiple times. So actually you can add a multiple masking period. But that starts to be a bit cumbersome to do it like this. What that's maybe good just to testing purposes, but if you want to, let's say, keep this information somewhere that you're gonna reuse, and that maybe if the next generation of people analyzing the data might want to reuse, you might want to keep this information somewhere. So especially if you do it manually, you want to keep a track of what you did. So basically, there is also a way to add mask periods. You see like the function, but with an S at the end. This function doesn't take as input a start and a stop time, but it does take a file as input. And this file contains actually all the mask periods that you want to include. And that's how we work in our lab, is that you see like multiple people might just chip in and then look at the same data and find different mask periods. Here I created one for this tutorial. You see like if you keep the original path, it's going to point to actually again the file that is contained within the and that file is exactly this one, is the example underscore mask log CSV, which is located in pyActigraphy test data. And actually this is what I describe in the notebook. This is the format. You have to respect the format, and then once you have when it's done, you can easily ingest it. So what it is, it's a file that has a single line header, which those names, which are reserved keywords, so you shouldn't change them. It's mask, start time, stop time, and remarks. The mask is just the mask name. You can give it whatever name you want for each mask period, then 0, 2, blah, blah, blah. Maybe you want to distinguish different mask type. And then the start time, please use the standardized time, because you see like, especially if you exchange data, you see like worldwide, you see we don't have the same convention to report a year, at least a month and day, and that's always, like the ambiguity. Is it the 1st of February or the 2nd of January? So just use the standardized way, which is like year, month, and day, and then the time. And that will save you from issues, especially if you exchange files. And then you have the start, the stop, and then you can put remarks. Remarks are not evaluated. It's just for you to keep track. Maybe you mask this period based on the sleep diary that was also filled during the data recording by the participant. Maybe it was just visual inspection. So if you want to keep track of these different remarks, you can put them on the fourth column, and that's not going to be evaluated, just for keeping track of the work that people do. Okay, so let's go back to the tutorial itself. So here I created one with just this one, and actually if you do it, it's like I won't change that, but imagine that we reset the mask. Here we don't have any mask, and then we said, look, I'm going to use that file, and then here it creates. That's exactly what it created. It read the mask file, found a mask period, and then created a mask. Okay. So, but as I said before, you see like it's something which is dynamic, the mask. You can create a mask. We don't touch the raw data. So actually, you see like it's not because you created a mask that is automatically applied. We let the user decide. So you can create the mask, tweak the mask, and then test. So there is actually a dynamic way of, there is dynamic way to activate and deactivate the mask. And that's actually useful because it will also convince you of the usefulness of what you are doing. So now if I just calculate a specific, you see like a variable, the IS, I will come back to that, the inter-daily stability, you see like this one is so much. Okay, for the moment, we don't care about the value itself. But you see like it's a certain value and we haven't activated the mask yet. This can be done. It's not because you define a mask that it's automatically used. You need to activate it. So you do row mask inactivity and you set it to true. Once you do that, you see like it's not massive change because we mask only a tiny variable. But still, it has changed. So that means that actually the mask was taken into account. And now in the computation of this variable, you actually took into account the mask. So this spurious inactivity period was discarded from the computation. This is what it means actually. But as I said, it is something which is like dynamic. So you can actually set it to false if you want. And then you recalculate the IS and it's going to be the original value that you found at the beginning. So it's really something which is dynamic. You can play with the masking, see how it improves your data, and then convince yourself that actually what you're doing is useful. So you should definitely clean the data because it has an impact on the variable that you will calculate. Okay. So far, so good. Maybe I can see here a question. Is there potential for the use of extract actigraphy from an Apple Watch? Yes, maybe not Apple Watch, depends on the Apple, but if they provide a way to access their data. Fitbit is also something which is widely used, and there are ongoing efforts in trying to extract those. It could be done. It's like the example that I showed for the Aura ring, and that you see like um, you it might be, I mean, from there, you said like it's not Fitbit or Oura Ring. I don't know for Oura Ring, but for the Fitbit, for instance, it's not a research grade device. And like this is always something that is put forward. I know it is true, but you see, like at some point when you can access like a million users and you can access a million users' data over a year, you see, like the power of the number is also something that it's worth considering. I'm not saying that the Fitbit is the ultimate solution. You know, like you always need in lab, highly controlled, with devices that are research grade. You see, like it's something. But if you can also complement that with like a larger scale analysis, I think it's we can always that would be useful. And we can always learn something. So that paper with the ring is I think showing that. Okay, so that was my answer to that question. Okay. Okay, so that was it for the masking. So take-home message is that you need to visualize the data, identify those periods, inactivity period, and then create a file, or at least reuse the template that is within pyActigraphy if you want, and then fill the different mask period that's a cumbersome work, but that's useful because you see like even a tiny period like this, which is like an hour and a half, I think, and then it has already a bit of impact on the variable that you want to calculate. So that's something that is worth considering. Okay. Now, I said that there are two notebooks. I will shut down that one and move to the second one. The second one actually illustrates also something that needs to be done on the data. Let's run the first. Let's restart the kernel. Yep, here it is. Then again, visualize one data. Let's take subject one. Actually, subject one is designed especially for that because I wanted to illustrate a point, and that subject one, that bogus subject is just meant for that. You see, like here, you can if you are used to see actigraphy data, you see like you can already see the circular modulation of the activity, and then you can see that up to January 13th. And then you see like we still have data, so we are not in the case where it's really spurious inactivity, or it's not a stretch of zeros. You see, like there is still activity, and then you have these remnants of activity at the end, and then there is no activity anymore. Okay, so that's something different. You see, like it's not like the participant, they remove the device for 1 hour or two, and then you can easily spot that because it's completely flat, surrounded by periods of activity. Here it's slightly different. It is sometimes depend on the protocol, but you see, like you might instruct participant to wear the device for, I don't know, like so many days. And but the recording is still maybe set up to do a little bit more, like 10 days. So, and depending on the device, sometimes you can also maybe say, look, I will start after the configuration. You can delay the start by so many, but sometimes you just count and then start to acquire data right now. But the participant is scheduled to come and pick up the device later on. So you have data at the very beginning that does not represent the participant activity. And at the end is also the same. Like maybe the participant said like, yeah, well, I'm done wearing the device. I will remove it. And this is it. Or sometimes it happened to us that if you request also, if you send device by post, by the mail post, like it was done in the UK Biobank. Also, you ask them to return the device by post, and you see like but the recording might still goes on when you return. So actually, we could see in some of the recording that we had in our lab, you could see that we could see some early activity, and it was actually the post, like handing the device and then it back. And actually, you could also see that people they actually drive to the lab and then they were returning the device. So it's really funny to see those patterns here, but the bottom line message is that it's not the participant activity. It's not something that you want to analyze, but that's not something that you can automatically discard because that's activity. It's just that you can see from the pattern that it's not the participant activity. So you want to remove, and usually those kind of data, they are at the beginning and at the start of the device, the recording. So basically, we have two ways of doing it. One is really doing the cleaning individually. You can chop the data. You can crop it when upon reading a certain file, you can say, look, I want to start at a specific date, time, and I want to read the data for so many days. So you see like here, if you want to read from here, like January 6, 7 p.m. up to again 7 a.m. on the 13th of January. So it's like 6 days and 13 hours, and you start here. So you can specify that upon reading the file. This is okay. Let's try it. Okay, you select the start is indeed where you specified it. The duration is also adapted. And then if you look at this crop data, exactly, there is nothing here and spurious and nothing here. So it was really cropped, chopped. And now if you do analyze this, then you don't have this kind of data that actually is not your participants' data. So that's something that you can try because you might want to visualize. You see, like it's easy to do, but now if you have 100 of files, that might be a bit annoying to have to read them individually like this, set up the start time, the period, and everything. So actually, we have another mechanism for that. Let me just finish here just to show you the impact on the data. You see, like this variable, this interdaily stability, this is really low, like this 0. Almost 0.2, and this was calculated with the raw data. So really this one that contained this spurious activity segment. And now this is calculated with the cropped one. And then you see like indeed the difference between the two is sizable. You see like the participant had a decent stability score. It's just that you were actually analyzing data that was actually not this activity data. So you need really to clean the data. But it's cumbersome to do it by hand. Well, you will still do it by hand, but maybe in a more efficient way. What we set up in as a mechanism in pyActigraphy is a way to read a file that contains this individual start and stop time, this SST log. I created one also for the workshop, but actually, if you look at the original example, again, it points to the file that is contained within the toolbox. And actually, those are the SST logs. So there are different file formats that you can use, Excel formats, OpenOffice formats, and the CSV. I always suggest you to CSV because there is no ambiguity, especially for the dates. If you use Excel, depending on how your computer is set up, you see like whether you are in the US or I don't know, in Australia or in Italy, you see like it might interpret the dates differently. And then if you save, then it will also save with this modification. So I would recommend if you have these Excel files, then you can still read them, but just like I would recommend to go for a CSV, which is like an unambiguous. It's just text. It is what you input. There is no interpretation. Now, if you look inside, you see like this is again just a table. Again, the header is something that you should keep like this. It has a subject ID. All those terms are keywords, so you shouldn't change them. The subject underscore ID, start underscore time, stop underscore time, and remarks. And actually, you can put here, it's the name that you actually get when you do this row name. So you get the name of the recording. You put that into that file, and then you can specify the start and the stop time. So that's the beginning and the end of the recording as you want to analyze it. Okay. And then you have a single file. So again, it's easier to maintain. You see, like here, we think, but you see, like we are always happy to discuss alternatives, but we thought it was a nice way to have files that are created within the data set. And then when you want to share the data set, you can share the data and you can share those companion files and say, look, this is the files where we put the start and the stop timestamps for all these different files. And maybe someone will just do another round and check. Maybe there were mistakes or disagreement between, and then you can just change the file and then you can use that file upon reading all the data. So you see, like it's a way to make permanent all the knowledge that you gather by visualizing, by inspecting visually your data. So instead of changing the raw data, which is sometimes something that you cannot easily roll back to, we decided to use companion files. So the mask files and the start and stop log files. So if you have ideas for alternatives, we're always happy to discuss that. Okay. Now let's discuss the format of the start and stop log. So here you can import from the log submodules, you can import the objects SST log. You can read already or directly read the SST log file. This is what we're going to do here. And then once you have this object, you can inspect the data are contained in the log attribute. And here it is. You see, like this is the file that I created. If you want, we can have a quick look at actually this one. If we go to data, and this is my project SST log, you see like a subject. I put subject 1, 4, and 1, which is named bad example. And here it is, just like a start, stop, and remark. Maybe the remark is, I don't know, again, based on your, I don't know, based on the sleep diary or based on visual inspection or something that you want to keep track, especially if you exchange data, might be handy to put remarks in there. Okay, so I created that file. I read that file here. You see, upon reading the file, it will calculate the duration. I always invite you to check that, or at least check the summary. Once you have this SST log object, you can inspect the summary. It will tell you, okay, look, on average, the duration of the recording after they have been chopped is so many days. The standard deviation is so much, the minimum, the maximum, and so on and so forth. It's useful because you see, like if you have really large data sets, sometimes we have data sets over, I don't know, a few hundreds of recordings, and then people use like they inspect visually all of them and report those. But you have to type the date, the timestamp, or the start and the stop, and you always make mistakes. It's like that's something which is like a truth is that you will always make mistakes. So it's always good to see because sometimes people they invert. You see, like if you are tired, you will invert the start and the stop, or do a missed a typo there and there. And that's easy to spot because sometimes you invert the thing. So if you see a negative duration, then obviously you see like you switched things, or sometimes just like you will see that the duration is maybe too short or too long, and then it might help you to spot bugs. Okay. So once you have this file, the thing is that you can easily read you can easily read that thing. Here you see like I illustrated so far the way to read data individually. But if you're interested in like reading data by batch, oops, sorry. Let's go back to the notebooks. There is one which is batch. If we have the time, I'll show you that one. But you see, like it's nothing more than instead of reading one file, it shows you how to read a bunch of files, which is ultimately what you want to do. So it's nothing more than instead of having this read row and then mesa, you can just set read row, input path. Here is the path plus, like the names, but here you can use wildcards if you want, you see, or you can use, you select specific syntax that tells, okay, I want to have all the files that are subject and then a character, which is actually a number between 0 and 4, and then .csv files. So actually all the files that match this pattern will be read. And then the type of the reader that is underneath to read those files is actually the Mesa one. If you are using, I don't know, the ActiWatch from Cantech, you can use AWD, and then Respironics is going to be RPX. I mean, you can change that to any type. Each time there is a read function, there is a reader type associated to it. Here we are reading Mesa-like files, and I'm reading, you see, like I was able to read all the files quickly. Now, if you want to inspect how many, because actually this is just a container of the different readers. If you want to access how many files you read, you can just access the reader object and see how many objects are stored. So it's actually a list of objects. So you can just look at the size of the list, and I'm just going to return. So we read 4 files, and then you have this reader. Now you can read the SST log. This is precisely what we do here. We have a function read SST log that will read that log file, and done. Now you can access it again, like we said, the SST, and then inside the SST you can have log. If you want, again, the summary, that's easy because you have the object and then you have a summary function. Again, it tells you, okay, look, this is what we saw before. And then maybe to illustrate that, you see, like it's nice to have, it's not nice, but it's even important to clean the data. You can calculate maybe the inter-daily stability, for instance. I'm always using this one as an example of things that you can calculate. And if you calculate based on that row reader object that contains multiple files, it will know that it has to calculate it on all the files. So these are the different files that we read. These are the names of the recordings, and these are the value of the IS that was calculated. And if you remember the previous tutorial, you see, like for subject 1, we had something which was close to 0.18. So here it is. We have this value. But like the mask, we wanted to have something which is dynamic, just to, at least it helps you to see what you're doing, that it's not because you created a start-stop log file and you read it, that it actually applied. You need to apply it because you need to make sure that you can find the file that are linked inside, or that are referred to inside that file. So when you actually apply, you can turn on the verbosity, and it will tell you a few things. A few things are actually that it will tell you, okay, look, I know that I have a file which is subject to, and I couldn't find any entry in the start stop. Maybe because you didn't want to. That's something, or maybe you forgot to. So that's why it's useful to have the verbosity turned on. It's because maybe you forgot. Maybe there is a mismatch between the name in the recording and the name that you put in your SST log. So it will tell you, okay, I couldn't find any entry for that subject. Is that normal? Maybe it is, maybe it's not, but at least it will draw your attention to it. And then it will tell you, okay, look, I found an entry for subject 1 and I found an entry for subject 4. So when you apply this and he found an entry, it will apply the start and stop that he found in the file. So those start, it will apply them to this individual file. So now if you recalculate this variable, this metric, then you see like it was changed for subject 1 and subject 4. So in the past, it was almost 0.18, and now it's almost 0.80. So, and that's much more to the, let's say, the value that you would expect from people of that age with that device. So that's why it tells you how valuable it is to clean your data. You need to chop the start and the end, and also remove the spurious inactivity within your recording. So I hope I convince you that it's a useful step. It is almost a mandatory step before any analysis. It is annoying by definition because you have to inspect, you have to type the start and the stop. But we tried our best to provide tools that once it is done, you can reuse this information, you can actually share this information because it's contained in a companion file, and then someone else can continue. Maybe you can split the data set in two and do the first half. A colleague will clean also the second half, or you can even share within the team. You see, like it might be a collaborative effort, which makes it easier. You see, like this is why we created a file. You can make it. It's much easier than just coding, hard coding or chopping the raw data, which means that if you revise your criteria to chop or define what the spurious inactivity period is, then you won't be easily able to change that. Okay, so that's the end for you see, like the cleaning of the data. So we are still on time. I hope that everyone is still on board, not completely exhausted from those tutorials. I think you see, like it's really extremely difficult to give you, like all the details about, like a full-fledged analysis. It's more like we are trying to give you this, illustrate the different aspects of what is implemented in the toolbox, but that you will definitely need for your own analysis. And then you see, like it might be just the foundation for building up your own, like a notebook, analysis notebook. And also there are plenty of things that you can do if you know how to manipulate data in Python. So, but hopefully, I mean, luckily Python is a really large ecosystem with plenty of tutorials, like resources. So you can easily find, once you see, like you understand that behind the scene we are using standard packages that you can that actually render the data in tabular way, and then you can manipulate them. You see, like you can do whatever you want actually with those. Okay, so that was for.
If we're at a
Yep.
if we're at a stopping point, do you want to answer there are two sort of questions that you can maybe answer in the chat?
Yes. Okay. Cool. So that's will give a bit of a break for people. I promised a tea break, depending on where you are, but that's maybe the right moment. Okay. Let's start with the first one. What algorithm is the best for studying children's activity in your opinion? Okay. That's a good point. Again, if you best, you need to quantify what is best. If best is something that has been validated, but again, validated with what? They validated with the PSG, saying that, okay, look, you want to have an output from your algorithm that matches your expectation from polysomnography. If you're doing that, the SADE algorithm is the one that has been validated in pediatric population. It has been recently revised by in a group in Zurich that is doing a fantastic work in infants. That's the group of Salome Kurt and Sarah Schoch. They publish papers on like different ways to also correct and improve this algorithm. So if you look at their work, you will find it, and that's the one that we use. Now that's best in a sense that this one has been validated against the PSG. But as I said, it depends. If you want to have something that actually you should, you see, like you use that one and use the SADE, but the SADE, you see, like long time ago, it was devised on a device that most likely does not exist anymore. If I remember correctly, even the acquisition mode was different than the one that is used in most of the device now. So you see, like it's always difficult to say like it has been validated because that's been validated in a certain context that is sometimes hard to translate to a new context. So that maybe you are as good as using that one than another one that is more suitable to your device. So that's really a difficult question at the moment. What I would suggest is the REST activity detection algorithm, they should just replace what you would do, but in an automatic fashion. You see, like if you are just interested in detecting REST period, and a rest period irrelevant of the fact that it's behind the scenes sleep, because the rest activity pattern in itself is useful to study or important to study. Maybe what you should do is that you should try to get what you want and detect yourself visually the different on a subset of your cohort, and then run the algorithm. And then you should tune the parameter of your algorithm so that it matches what you expect. And then you see on a small other sample if the testing is successful, and then you can maybe run on the full cohort. So like it's the classical validation of a trained set and then test set. That's something that actually we should do, or at least have guidelines on the different device. You see, like tuning the different algorithms, because they have always input parameters that we can tweak. So it's really difficult at the moment. There is no good answer, to my opinion, out there. So maybe that's something that should be developed, a pipeline to help people to tune to their own population, or at least provide guidelines. Okay. The second question is the IS calculated taking into account all the days of data we have? Yes, it is. The IS is actually the intraday stability. It compares every day to the average, the daily profile of that participant. So if you do exactly the same thing every day, given the resolution that you input, so if you put a resolution of 60 minutes, so it means that you should have a quantity every 60 minutes, a movement quantity count number, which is the same every day, then you have an IS of 1. If you never do this, so it means that the average actually not representative of any day, which is the case in the case of a white noise, you have an IS of 0, which is not physiological, but it's just to tell you the two, let's say, boundaries of the IS. So this is what it does, actually. Okay. I hope I answered the question. Maybe that we are done with the the cleaning. Maybe we can move on to the let's say something which is more recreative, a bit funnier, closer to the actual analysis that we want to do. Sometimes we want to, once we have the data, you want to automatically detect the rest activity periods. Again, this is with we implemented different algorithms in pyActigraphy. You see, like at the moment, I think there are like 1, 2, 3, 4, 5, 6 of them. The purpose of actually implementing all of those, it's actually because sometimes by comparing them, you can grasp already the variability and the ambiguity that there is, because you will get different outputs depending on the algorithm. So that's also helps you to gauge, okay, let's say the robustness also of the detection. So that's also useful to run multiple ones. And also they have sometimes, like we said, some of them have been validated in specific populations, or they have different features that you might find relevant for your analysis. So at least you have the choice. I'm not so sure that there is other packages that can implement those, and I would like actually to keep track of the new developments, because that's also something that would be nice. So if you are keen on collaborating and you want to implement new algorithms, that would be also something that would be nice to do. Okay. Okay, let's do this. Again, with this notebook, we start with importing the package. We import also the visualization package. And then again, we read one of the test data that we sent around. Here it's going to be subject 5 for illustration purposes. Concerning the detection algorithm, we classify them into 2 different categories. Maybe there are more than this, but actually it's like to my opinion, there are just 2 broad classes. The first one is the one that is, and you can feel already from the terminology that it was really inspired by the PSG. It was just to somehow emulate the PSG. So the scoring happens like on like on an epoch by epoch basis. So it tried to score every epoch of 30 seconds. Okay, is it rest? Is it activity? Is it wake? Is it sleep? So that's really like you would do in any EEG or scoring. So every window of 30 seconds, then you will say, okay, that's stage 2, that's stage 3, that's wake, that's REM. So do you see that the way it was devised is really like it's almost PhD oriented. And those are for the Kolle-Kripke, the SADE, the Scripps, and the Oakley algorithms. For instance, some of them, if you use, like proprietary toolboxes that are shipped with the device, I think in the motion, the Camentech, the Respironics, they use those algorithms. The Oakley is used by Respironics. Scripps is used by another one. So you see, like it's actually the standard really detection algorithm that are on the market that we have implemented. But here you can modify also the input parameters. Basically, also what you should be aware of is that the idea behind the scene is to me, when I implemented them, you see, like if you take a little bit of distance, then you realize that they are always based on the same idea. The same idea is that you have a window that you slide along your recording, and then this window is centered around the epoch of interest, and then it computes the data, the activity data, a bit before the activity of interest, a bit after, and then tells you, okay, look, well, it's just the activity or some computation based on the activity. And basically it sets a threshold and say, look, okay, if the outcome of the computation within that window is above the threshold, I will classify as, I don't know, wake. If it's below, meaning that the activity is low, then I will classify as rest or sleep. And basically it's the same. What basically changes between the algorithm is that, like, it's the shape of the window, the different weight that are let's say assigned to the different epochs a little bit before and a little bit after. But well, the broad idea is roughly the same, and they score every epoch like this, which is, to my opinion, it's nice because it's super sensitive, but it's also a caveat somehow because there is no start and stop. It's every epoch is scored. So let's start with the Kolle-Kripke, just to illustrate what I'm saying. The Kolle-Kripke, if you type help, then it will tell you, it will also give you the reference of the validation paper, some, let's say, details on the implementation. You see, like, those are the weights actually in the window, and you will see, like, it's actually like almost like like a Gaussian, like let's say, kernel. We have also implemented the Webster's rescoring rules because indeed it does correct after you classify them. It does some correction to the classification. If you have a stretch of let's say epoch scored, I don't know, wake, and a single one which is classified as rest, then you see, like, maybe you want to rescore that one because it was a hiccup or something like this. So there are rescoring rules actually for that. So running the algorithm is as simple as doing, okay, I have my row object, and then CK for Kolle-Kripke, and then it gets you back again, if you want to inspect what it is. It is a time series also with a timestamp, and then here it's 0 and 1, just classification per epoch of your REST activity. And if you want to visualize it, oops, maybe I forgot. Where is the, yes, here it is, hidden. Yep, layout. And then here it is. You see, like, it was, so in red, we have the scoring. And as I said, it's every 30 seconds it was scored. So that's why you have also, it can be scored. Yes, it is inactivity or rest or sleep. And then it's activity, inactivity, inactivity, and then so on and so forth. So every 30 seconds you get a score. But it's hard to track. You see, like, you can have the metric, so over a certain period, how many epochs of wake and sleep, but it's hard to track when it starts. So that's what actually, you see, like, we implemented also another class of algorithms. So here it's for the CK. If you want also to have a look at the SADE and script, again, is as simple as running SADE or script function, and it returns the scoring. Once you have the scoring, you can analyze it the way you want. Here it's a scripts. It's a bit messy at here. And then if you want to look at the SADE, but you see, again, but what it tells you already is that you see like it's really, really messy. It's hard to distinguish there. It's maybe because that specific device, you see, I had a way to calculate the activity, the counts, maybe the linearity of it, like it is something which is not suitable for that algorithm. Maybe that algorithm is too sensitive and will say, look, are insensitive and say, look, each time I see something which is a bit too low, up, and then it will classify this as inactivity. So you see, like it's really hard to I think it's really hard to use those things because they have been validated, but you see like it was different devices. You see like for this one, it's device that was run on the 1 minute period. And the acquisition of, I think it was like the zero crossing mode, for instance, which is not the one that is used in most of the device on the market at the moment. So it's always hard to, but it makes sense. Just like the paper dates from, I don't know, it's like 82 and for 92, sorry. So you see like it's a long time ago. So it's like 33 years. So that makes sense that sometimes it's not extremely suitable for your own needs. So you would actually be better by maybe tuning. So it goes back to the discussion that we had on the best algorithms for infants, for instance. So that's really a tricky business. But but at least if you want to tune, if you want to modify some input parameters, you always have these input parameters. Look at the maybe type the help for the whole SADE. Oops, SADE. You see, like by default, it uses the parameters that are in the validation paper. But if you want, you can actually change. You can change the offset. Maybe you should tune the offset to your population. So that's something that you will be that is easily available within the package. Okay, the same for Oakley. Oakley package. This one is used in Respironics, but the thing is that like Respironics, they have specific counts. So so the maximum is set to a certain value, the minimum to another one. So they can put an absolute threshold on and say, look, yes, that corresponds to that type of activity. So actually, in you can within their software, you can set a threshold, and here it's the same by default. It's the median threshold, but you can adapt. Or there is a way also to adapt the threshold to your population. So here it's also something that we implemented. If you look at the 30 is the default, but you can also set it to, and then there is some details also on how the automatic works. And then also the weight of the different, let's say, the weight within the Gaussian kernel that is used to score is also different depending on the sampling frequency. Everything is actually, let's say, set up nicely within our implementation. So it matches what you should get actually with the official software of Respironics. Okay, so with the automatic one. So let's see what it does. Here it's the automatic one. Maybe what we can see is that maybe it's a bit less sensitive, more specific with the automatic threshold. So you see like it boils down to the discussion we had about the fine-tuning of the algorithm. So you see like here, exactly this. It's like someone that was really active during the night, but maybe those small periods, you don't want to classify this as sleep. You see like here, just because you had only one, you see like it doesn't make much sense. So that's the kind of specificity and sensitivity trade-off that you need to take into account when you tune your algorithms. Okay, so those algorithms, they are on the market since quite some time. They are still widely used, so that's why we implemented them. You see, like they are useful. So don't get me wrong, but you see, like there are another class of algorithm that we also like, and we implemented them. It's actually it's more like maybe well, to say chronobiology oriented in the sense that it's not really, you don't care if it's every epoch. What you want to know is this main rest episode, where is it situated, or, like on your, within your 24-hour pattern. So actually those algorithms, they search for consolidated period of inactivity or activity. So, and they give you access to a nice feature is that they have a start and a stop. So that's also something that might be useful. I think the first one that I implemented was the Crespo algorithm, which is actually nice. The only thing is that the Crespo algorithm is really useful, but it makes some assumptions. So if you have a population that is really like let's say you're not standard, but habitual population, like no shift work, like it sleeps around so many hours during the night, not too variable. Actually, it does a good job, but you see on population that are a bit like a bit peculiar, or at least off of the expectation of that algorithm is might do actually not a good job. So you have to be careful with that one. Obviously, there is all those input parameters that you can tune that have been set up to the default values that are the one used in the validation paper. But if you want, you can also modify them. Here, it's what we do. Like the main episode is for maybe older population, something which is closer to 6 hours than the 8 hours that was put, for instance. And here also is something that you try to estimate also from the data, the distributions of the different stretches of zeros that will help the algorithm to find the inactivity period. Okay, so that's it. And then this is what it gets. And you see, like, compared to what we got before, we don't have an epoch by epoch. Here we have a window that has a start and a stop. And that's something that is actually something which has a nice feature, because you might want to say, look, I want to know. And then maybe within this rest window, you want to do something. But for that, you need to identify it. You need a start and a stop, which is much more difficult if you get something like this. So when does it start? When does it end? Like you can see that here start to be consolidated, but in an automatic fashion to detect that thing is there. It's maybe not that easy. So it here, but here you can see that if you change the it make a sizable change here. So that's why we said you need really to adapt maybe the input parameter to your population. Because most likely the population that has been used to validate the algorithm is not the one that you're interested in. So that's always there. Murphy's law somehow. Okay. Another things that we have implemented for those two is maybe a shortcut, because actually once you have this Crespo, you select the one that I display. It's a time series with 0 and 1. So actually you can compute statistics based on that. It's just data manipulation from just a standard tabular data. So if you know how to do it, then you can easily do it. But what we wanted to ease a little bit this, and actually we have a function. Each time you have an algorithm, Crespo, or the next one, which is Ronneberg, you have this AOT is like for activity or offset or onset. And actually those are the onset and offset times. So it does calculate actually the onset and the offset here of each window that has been detected. And this is what it does return here. And the first one is actually the activity. The first one is the activity offset, and the second one, the activity onset. And then by differentiating the two, you can get the duration of each episode. You see, like the second episode was long of 7 hours and 25 minutes. The first one was 1 hour, I suspect, because it was the beginning of the recording. Yep. Exactly. The only thing that we need to pay attention is that what we decided to do is that we haven't harmonized the different software algorithm. We kept the original implementation. If the original implementation is that 1 is activity, we kept 1 as activity and 0 as inactivity. You will see that in the Ronneberg one, it's the opposite. We wanted to harmonize everything, but we said that then it will be confusing. The ground truth is the paper that describes the algorithms and the validation. And actually, this is what we implement. So there is no ambiguity. You can change it if you have access to this time series of 0 and 1, and you can easily invert it yourself. But that's your choice. What we decided is not to change the way the algorithm was implemented, although it might be dense algorithm dependent. Okay. So here it's like that's why it's like this. So the window that was detected is the activity one, and in between you will have the inactivity. So the rest. Okay. So now we end up with the Ronneberg algorithm. Actually, they're my favorite one because it's the one that out of the box gives you the most reasonable, let's say, results. And also that's the one that is easy to tune because you see like the most sensitive parameter is the threshold. You can look at the implementation, the paper, which is listed here at the end. You see like it's the one describing the algorithm. This one is the one validating it. When they validated it, they call it the Mazda. So you can find it on the market as, we call it the Ronneberg algorithm, but now it's the Mazda algorithm. And that's the one, it's like you can change all the parameters, but most of the time what you have to change is the threshold. So it's the sensitivity of detecting rest or active periods, okay? But out of the box, it does a really good job. I think by default, the threshold is 0.15. So it's 15% of the median over 24 hour. On this sliding window of 24 hour, here the threshold will be set at 25%. Just to see the differences, and then there we will start to consider if it's a rest period, if there is a stretch of inactive periods of 15 minutes. So that will also increase the sensitivity of it, and then you can see, but maybe it will be too sensitive. Here it is. You see like this one also display nicely. This is the one I like because out of the box it gives you the window that I would have done manually anyway. So, and this is for me the purpose of these kind of algorithms. They just do in a reproducible way what you would have done by hand. You'll see like detecting this kind of inactivity period. Here, a small one was detected also. And it was detected by the one that has a smaller seed period. So, but you see like not by the one by default. So it's also up to you to tune these algorithms to your need. If you want to be more sensitive during the day, if you want to detect naps, for instance, that's also something that we did. And here is like the threshold will play also a role on when you start to detect the inactivity. But overall, you see like this kind of windows by this masked algorithm is most of the time what I would have done. And here you see like it was interrupted during the night and then split the rest window in two, and that seems reasonable. So, but you should always inspect what has been given by the automatic scoring. Okay. And again, like for the Crespo, we have this automatic detection of the onset and offset time, which are just like when you have a transition from activity to inactivity, and this is as easy as the same signature of the algorithm itself, except that you put underscore AOT at the end, and it returns the times. And again, the times are the dead time for each onset and offset separately. So you have the two, and if you differentiate the two, then you get access to the duration of each window. So the first one was the 8 hour long. The second one is the small nap that we or nap, or at least could be a nap that we detected. And then you see like every day we had, except that one that was split over, like 2 periods. And then, but overall it was consistent with their 8 point something hours of rest at night. Okay. And that's it. You have this, you have the time series, you have the time for the offset. You can compute any kind of a metric that you want to have. You have the sleep duration. There is also like the sleep regularity index, which is also a nice feature. It is implemented in the package. We don't have the time to cover that one, but it is in the online documentation. If you browse, you can find it. This one is also something that can easily be used. So there are plenty of things that we can do now If you have ideas on, like a metric that you would like to see reported here, or maybe a way to standardize the output of the different algorithms, if you have ideas, please come forward. That's something that we would like to also to hear from you. Okay, so that was it for the REST activity algorithm, detection algorithms, automatic ones. And also, yes, like I mentioned, if you are keen on implementing also new ones, that's also something that I think is worth, because the more we have, I think the better, because there is no universally good one. It depends on your population, depends on what you want. So actually, there are room for new ones in that respect. Okay, let's shut down that one. Okay. Am I on track concerning the time? Maybe I see here that there is questions. Are there any plans to be able to manually correct any of this classification? Well, okay. So depending on the algorithms, as I mentioned, there are already some rescoring rules, but since they are specific to, but maybe I didn't foresee that they might be used outside of their initial implementation. So it's like for the Color-Kripke, it's actually implemented within this Color-Kripke, the Webster rescoring rules. But they are maybe more generic than just like the Color-Kripke classification. They might be used on top of any of this epoch by epoch. So actually, they should have been decoupled. But it's always easier to see what you should have done after. But indeed, that's something that should be done to have a module that can actually help people to rescore automatically the scoring, and maybe be able to tune the way you want to rescore the scoring. So maybe define your own rules, saying, look, yes, if I have a stretch of so many minutes of wake and a single epoch of rest within, then rescore it as wake, please, because you see, like, you don't fall asleep for 10 seconds and then go back to wakefulness, or at least it might be possible, but from the activity point of view on the resolution that you want to study, maybe it doesn't make sense. So that's something. The other part of that question will be like, if you want to rescore manually, actually you see, like, any output of those algorithms is a simple time series of zeros and one. You have it. Let's see. Maybe I need to restart the kernel. Sorry. I restart the kernel and I would execute all this. Let's see. For instance, SADE, and then the SADE and the. So as I said, actually, you see, like, you have. Did it restart? Maybe I should. Okay, sorry. Okay. Let's restart everything up. Yes, okay, we have it. Okay. So you see, like, for instance, the CK or SADE, whatever, you see, like, it's a simple time series of 0 and 1. So if you want, this is what I visualize here. You see, like, this red thing. So actually you have. So basically, once you have, you can access any of, it's just data manipulation. So if you want to access your data between, I don't know, that time and that time, you can actually reset the values inside and then use that and then compute any metric out of it. So it's like you can actually change that, but I do admit that it's a bit cumbersome. That would be nice to have a visualization where you can maybe scratch. But you see, like, this is what I said at the very beginning, the visualization of the this, maybe also for the masking, having something visual where you can just click and say, look, yeah, from there to there, I want to mask. That's something that would be extremely useful. The problem is that this kind of graphical interface is something which is, I mean, you need some time to dedicate, and maybe some a priori knowledge that I don't have, or someone willing to learn. But that would be extremely useful to have. It's just that, like, it's a project on its own, but that's something that would be extremely valuable. I agree. Yep. So you can do it manually at the moment, but maybe we need other tools to do it in a more, let's say, pleasant way. Okay. All right. Maybe I will ask my host how much time we have left. Maybe depending on the stamina that is left in all the participants. There are maybe another things that we can quickly see. Or
Maybe another like 10 minutes or something like that, and then we can
yep.
go to the breakout room.
Yep. Yeah, something that I like. Maybe I will show you because okay, well, I prepared it because you see, like, I wanted to show it. This one I like because you see, like, first time that we encountered the a metric in one of the proprietary toolbox that was shipped with a certain device. We could see fragmentation and things like this, and then it was okay. I was excited, and then I look at the definition, and the definition was really crude. And we're like, okay, the fragmentation index is not what I would expect a fragmentation is, or at least when you look at the data and you say, like, look, that's something that shouldn't be considered as a fragmentation. You see, like, if you consider every movement a fragmentation, then obviously your sleep is fragmented because you do move during sleep. So it's a bit more complicated than just counting, like the counts within a period of inactivity. So, and actually, I was surprised because there was a paper by Andrew Lim, and so he's an MD, and I was surprised because you see, like, not that I'm not saying that MDs are not really keen on mathematics. It's just that I was just surprised of saying that the actual solution, the elegant solution of that would come from not a mathematician, but an MD. But I think it was also unsatisfied by the way fragmentation was quantified so far. So it came up with the idea of that you need to use state transition analysis to quantify the rest activity fragmentation. That made completely sense. And they implemented that. And it was we implemented it, and actually we could compare because Andrew Lim was kind enough to share his code, and then we can compare our implementation based on the paper to his initial code, and it does match. So for that one also, that's I'm quite grateful because not everyone is keen on sharing codes. So that was a good one. Okay, so for the rest to activity transition probability, the basic idea behind the scene is to say, look, I will look for stretches where you are in a certain state, let's say rest, and I will count the number of transition to wake. But you do that over the whole recording, and then you start to build up some statistics and say, look, as when the stretch is that long, I found that you transition so many times. When the stretch is that long, then so many times. And actually, you can compute the whole distributions of that probability as the function of the time that you spent in a certain state. So this is exactly this. So you see, like here, if you want to do this, we have, again, you read your data, subject 1, for instance, for these 7 days, and then you can use this PRA. So RA is for transition from rest to activity. And then you can say, look, I want to analyze data that from midnight to 8 a.m. By default, you see, like, you don't have, you can just put anything and it will use the entire period. But if you want to focus on a specific period and select, that makes sense because that's maybe the time period where you are most likely to be at rest and you want to quantify that is what is your probability to transition to activity. Then that would be fragmentation because you are supposed to consolidate that state rest, although that you might move from time to time. You can say that it maybe the smaller transition will be relevant. So you have to look maybe on average if it does transition after a certain time. And then you can calculate this and plot this. And this is exactly what it is shown in the paper of Andrew Lim, is that just like it does decrease like this probability as a function of the time that you spent. And actually, when you start to reach a certain amount of time, this is when you are engaged in this sustained activity or rest. And then this is the probability that you will transition when you have attained a certain amount of time spent in that state. And actually, this is what is fitted, this flat, let's say, this plateau in the curve. This is what is fitted, and actually this mean value over that plateau is actually what is returned. So here the K, so this is the name that was given in the original paper, this K RA for rest to activity. If you look, you see like it's around 10%. This is what you would expect if you would fit something along those lines here. You see like, so you have 10% probability to transition to activity once you have attained a sustained inactivity period between midnight and 8 a.m. So that's really your fragmentation metric. So actually, you see like in pyActigraphy, once you have read the data, it's as simple as one line, K, RA, and then here it's the threshold. If you look at the paper, then you will understand what the threshold is to binarize the data. And here it is. And the nice thing is it was shown that you see like this metric correlates, obviously with aging, but it also correlates with the incidence of neurodegenerative diseases. So that's why they implemented that. I think it was the aim. So that's why I like that one. It makes sense from the physics point of view. Or at least it's more suitable than the definition that I've seen so far. So this one is a good. You can also say if you want to play with the like the window that you investigate for the rest. You can say, look, I want to look at the transition of rest to activity between, I don't know, 10 p.m. and 6 a.m. or something like this. And you see like it doesn't make much difference because actually all the rest periods are found with, like most likely during the night. So even if you look on a larger window, you won't find those stretches of rest. So you see like they won't contribute much. The additional one, so at the end of the day, it doesn't make much sense. Also, this was a conclusion in the paper. So this metric is quite robust and quite informative on the rest to activity. And conversely, you can also look at maybe where it is. Yes, I have it. Yes, it's there. So I won't discuss it here. There are other options here. You see like the thing that I discussed so far, like the activity onset that is tailored to the participant based on this daily profile. Maybe this is because you want to target really his own rest activity. You see like it does change a bit. And then conversely, you have the KAR, which is the activity to rest transition probability. So this one is most likely driven during your activity period, and it actually the opposite is that it looks for stretches of activity, and then as a function of the time you spent, it will calculate your probability to transition to an inactivity state. Something that is below the threshold that is set here. And then obviously it's like it's this, then you can also set these different keywords, or you can tailor the window that you look at, and voila, this is it. So actually it's a nice one. I encourage people to use it instead of look at if you're using fragmentation index, look at the definition, see if you're happy with it. And then if you want, you can transition. And you see like it's not that difficult to calculate. You read the data, you just calculate this, and then you see like that's easy. So that's something that might be worth investigating if you're interested in fragmentation of rest and activity periods. Okay, so that was it for our tour of the different things that I've left behind. The batch one, because this one is really well, it's easy. You see like instead of reading one file, you can read a bunch of files, but actually it gives you the same functionality. Behind the scene, you see like it's just the containers of different readers that you can actually access. So basically, you see like if you understand how to read and use a file, that thing is just a simple extension of it. So I have a tutorial on that. You see like you can have a look at this. Once you have it, you can make a loop of all the objects that you have read. So you can really do what you do on an individual basis. You can really do over your entire cohort. It's not that difficult. We have sometimes for some of the metrics, we have shortcuts. You give that on a reader that contains multiple files, it will give you multiple values. So, but it was difficult to implement all of them because they have different input So there are some times where you just need to make the loop yourself, but that's not that difficult once you have read all the objects. So this one I left behind. Another one that maybe is worth, well,
We can
you
also
can
go over
see.
more of these in the breakout session if you want.
Yeah, okay. That's there is more advanced processing things that we also set up here, but it's we need to master the basis first. So this is what we wanted to highlight today. Okay, thanks a lot. It was maybe a lot. I know that it's really codey because we discussed that already with Mike. You know, like it's always nice to have a graphical interface, but we can discuss that during the breakout session if it's really too much for newcomers or not. Just like I think you need a decent you need to invest time in learning data manipulation during your PhD. I think it's worthwhile. It's worth doing it during the PhD, but we can have different opinions on that. So you let me know. Thanks a lot for your attention. I hope it was useful.